All right, guys. Lesson 4-4, this is our last lecture in Module 4. That's obviously a total of 4 lectures. This is going to be called Dynamics Part 4. Really what it's covering, as you can see from the objectives, is we're going to be solving problems that involve both friction and inclined planes. Okay, so we're going to start with the friction, and then we're going to throw in friction and inclined planes. First off, let's talk about friction. So until now, we've pretty much ignored friction, and we've said that we are pulling objects along a smooth surface. But in most practical situations, friction has to be taken into account. Because while we do pretty much neglect air resistance for the entire course, we can't neglect friction because friction just affects the forces way more than air resistance does, okay, generally speaking. So what's happening and what's causing friction in the first place? I have this visual here. It's kind of showing you that no matter how smooth you think a surface is, there's always going to be some always going to be some bumpiness to it, or some like weirdness to the surface to where it's not perfectly smooth, all right? And even if it was perfectly smooth, physicists that actually study this notice that even if something is almost perfectly smooth, at the atomic level, when two things are touching, they are doing some weird stuff and actually connecting to each other in a way that causes some extra force to break that apart when you want to move it. So there's no way we can have a perfectly frictionless surface if two things are in contact with each other, right? So at some point, even if it gets very small, there's always going to be some friction, all right? And while there is a way of calculating friction in wheels as they're rolling, and we actually do call it rolling friction, we're not going to be considering rolling friction in this lesson. What we are going to be considering is sliding friction, or when objects are trying to slide against each other, okay? Mostly we just call this kinetic friction. Mostly we call this kinetic friction. So when an object is sliding across a rough surface, the force of the kinetic friction always acts in the opposite direction to the velocity that the object is traveling, okay? Now, I have this visual here for you, okay? If the net force was in this direction, hey Renee, if the net force was in this direction, then the friction force must then be in the opposite direction to that F sub A. All right, so experiments from physicists that study this show that force is approximately proportionate to the normal force between two surfaces. Okay, what I just said is that the normal force is the most significant factor that contributes to how much friction two objects experience. All right, the normal force. So what we say then is that if we're trying to define our friction force, we can set it equal to the normal force. That should actually be an F right there. The normal force times some constant. And that constant is going to be dependent on exactly what the surface is made of. Obviously, a smooth tabletop is going to be more rough than is going to be more smooth than the concrete, right? All right, so this weird sign right here, this weird coefficient in front of our normal force, is going to be different for different materials. That variable, that weird looking variable, is actually a Greek lowercase letter mu, and it kind of looks like a U with a kickstand on the left side, all right? We have it mu sub k to let us know that that is going to be the coefficient of kinetic friction. Different materials have different coefficients of friction assigned to them, and if you ever have a problem that's asking you to calculate friction force on the AP test or just on any other exam or homework, it'll probably give you what the coefficient of kinetic force is, or it'll tell you to find the coefficient given all the other information. And when we're talking about the coefficient, we are talking about that mu sub k, at least for kinetic force. Here we have a table that kind of lets you know different coefficients of kinetic force and different coefficients of static force. Notice that wood on wood has something like 0.2 for kinetic and 0.4 for static, but ice on ice would have something that was significantly less. Clearly ice on ice would have a lower coefficient of kinetic friction. Something that has kind of a lot rubber on dry concrete, if you think about that, that's clearly going to have a lot of friction. That's going to have a higher coefficient of kinetic friction and a higher coefficient of static friction. Another thing I want to point out here, guys, static friction is always higher than kinetic friction. When I say static friction, I mean the coefficient of friction that's being applied when an object is sitting still. All right? You guys have all experienced a situation where you're trying to maybe move a piece of furniture, and it's actually harder to get it moving than it is to keep it moving. That's because an object always experiences more friction when it's not moving. All right? So that's why we have different values for our coefficient when it's static versus when it's kinetic. Kinetic just means moving, guys. Kinetic just means moving. All right? Let's revisit that relationship now that we've discussed the coefficient. We just said that that relationship was the force of friction is equal to whatever our coefficient is for the material we're sliding on times the normal force that our object is experiencing in that situation. All right? And that's going to be the same for static friction, except that instead of U sub k, we'll have U sub s for the coefficient of static friction. Mu sub s refers to the coefficient of static friction, as I said, which is always larger than mu sub k. If it's asking for how much force is it going to take to begin moving an object, then we will use the U sub s coefficient as opposed to the U sub k coefficient. Again, because static refers to an object that is not moving. In reality, though, static friction is an inequality, because naturally, if I have an object that's just sitting on a table and no one's applying any horizontal forces to it, what is its friction force? Zero. But the moment I start applying some force to it, its static friction force will increase to balance out the force I'm applying until I reach the point where I have overpowered the static friction force and the object starts moving. So in reality, we have an inequality if we're trying to talk about static friction. All right? The friction force can be as low as 0, but it can only be up to mu sub s times the normal force. Once our force applied breaks this, then we break our static friction. And when we break our static friction, then we no longer consider it. It immediately transforms into kinetic friction, and we swap out U sub s for U sub k. Let's consider a situation. Remember, guys, when an object is not moving, then its forces must be balanced. Let's consider this 10 kilogram box, all right? So I'm going to say that it's 10 kg. It's resting on some horizontal plane, so I know that whatever force due to gravity is pushing down, the normal force must be pushing up with the same magnitude. Agreed? Very good. So let's assume we're going to apply some force horizontally to the right. Then there must be some force of friction that's pushing in the opposite direction to the left. That's going to depend on whatever the static friction coefficient is and whatever the normal force is. All right? In this case, it gives us both. So if we know that our object is 10 kilograms, can anybody tell me what our magnitude of force due to gravity will be? 98, exactly. 10 kilograms times 9.8 meters per second squared will give us 98 newtons. So m times g should give us 98 newtons. And that means that the normal force should have the exact same magnitude. All right? If this is negative 98 newtons because it's pointing down, then the normal force can just be positive 98 newtons. Does everybody agree? Good. So now that I know my normal force and I know my coefficient of static friction, if I just take the product of those two values, then I have my maximum static friction force. All right? That maximum static friction force would just be as simple as multiplying 0.4 by 98. 39.2. All right? So I know that my maximum static friction force must be equal to 39.2 newtons. That doesn't mean that it is always 39.2 newtons. It means that it'll match whatever horizontal force I am applying until it reaches 39.2 newtons. Does that make sense to you? So then here's my question. if F sub A is equal to 0 newtons, what is my friction force?
0.
0 newtons, exactly. If F sub A is equal to 10 newtons, what is my friction force?
10.
10 newtons, thank you, okay. What about if it's 20 newtons? 20 newtons, and then here's the fun one. What happens when my static friction force, what happens when my F sub A reaches 40 newtons?
39.2.
Ooh, that's what I expected you to say. We've broken our static friction force.
Is it 12?
It's going to be, friction force, in this case, is going to be 98 newtons times 0.3. Wait, yeah. So we should have 29.4 newtons. All right, that's a little bit weird. So if anybody has any questions, that's okay. Go ahead and ask them, please. Yeah, go ahead.
So I was just a little bit confused. So what were you asking for when you were asking about the different ABC?
Yeah, so ABC, we were applying a greater force as FA. And so at all three of those points, our static friction force was enough to balance it out. So we weren't applying enough force to move the object.
Okay.
But as soon as we hit 40 newtons, or in reality, as soon as we passed 39.2 newtons, then we broke our static friction force.
So you
And
change it to the coefficient.
so now we have a moving object, right? We have some acceleration, and so that means our friction is kinetic, and we have to use our kinetic coefficient. Okay? Make sense, guys? That's a tough one to kind of get past for your first time, but I think you guys are doing a good job of understanding what I'm saying. So that's that, and we could then move on to determine the net force and find the acceleration of the box. Okay, but we've done that enough. All right, let's go ahead and move on to what happens when we are sitting on an inclined plane. So here's the weird thing about what happens when you're dealing with an inclined plane. When you're drawing your free body diagram, you're gonna wanna rotate your X and Y coordinate system so that your X-axis is parallel to your surface and your Y-axis is perpendicular to your surface. So that's just a good rule of thumb moving forward in all free body diagrams. Whatever surface we're dealing with, we want our X and Y axis to kind of go parallel and perpendicular with that surface, even if that surface isn't perfectly like horizontal and vertical. Make sense, guys? So you'll notice that Y is literally pointing kind of diagonally, and X is pointing down diagonally just so it'll go along our surface. Everybody see this? Good. That's going to be very helpful so that we don't have to do quite as much trigonometry, even though we're on an incline. Now, what you'll see here is kind of a free body diagram for this box. All right? There are going to be three forces acting on it. There's going to be the force due to gravity that's still working perfectly downward. But the normal force is only going to be perpendicular to the surface. So we have our force due to gravity here, equal to mass times acceleration due to gravity. And then we have our normal force. This would indeed be equal to the vertical component of our force due to gravity. Then we have our friction force. Those are the three forces acting on this object. But there is a force that's acting along the x-axis, and that's going to be the horizontal component of our gravitational force. Okay? So it's still gravity that's causing our object to slide down the ramp, but we can't say that the net force down the ramp is equal to gravity. It's only equal to the horizontal component of gravity. All right? And it's the horizontal component of gravity because we have adjusted our XY coordinate system so that the pointing down the ramp is perfectly horizontal. Now, let's solve a real world problem. We have a skier skiing down a slope that is measured to be 30 degrees from the horizontal. Okay, this is just a photo. All right, so this is definitely going to be a case in which drawing a good free body diagram is going to be helpful for solving the problem. All right, so I'm going to first off start by drawing some incline that could represent the slope. All right, and I'm also going to do like this horizontal line so that I could show that we're dealing with a 30-degree incline. All right, so that's my first step there. Then I'm going to go ahead and kind of draw my x and y coordinate system just off to the side as a reference so that I know which direction is positive x. I know which direction is positive x, and I know which direction is positive y. All right. Once I've done that, I'm going to go ahead and draw a box to represent my skier. Okay, so this little box here just represents my skier. The only other bit of information that the problem gives me is the fact that we have some coefficient of kinetic friction that's equal to 0.1. All right, we don't have mass. We don't really have any other information. But it's asking us to find out what her acceleration is. All right, well, let's start just kind of setting up more of our free body diagram and see if we can come to a point where we've decided that we do have enough information to find what that acceleration is. It's going to be an exercise in algebra, okay, and a little bit of an exercise in the right triangle trigonometry that we've been working on up to this point. So, an object on the inclined plane, the free body diagram for that always kind of looks the same. All right, I'm going to use purple to show the force vectors. There's going to be one that's going straight down. That's just going to be force due to gravity, right guys? Force due to gravity. All right. There's going to be one that's perpendicular to the surface. That's going to be normal force, correct? Okay. And there's also going to be one that is in the opposite direction to the motion of the skier. That one is going to be our force of friction. Those are the three forces acting on our skier right now. It's also going to be useful for us to find the components of our gravitational force because, first off, the vertical component to our gravitational force is going to be what is creating our normal force. And the horizontal component to our gravitational force is going to be the force that is pulling our skier down the slope. Okay, so the way that I do that is I like to consider the fact that while this may be the force due to gravity vector, it's pointing in the correct direction. If I want to still do the right triangle trigonometry that I've gotten used to, then I'm going to go ahead and draw this triangle. All right, are you ready for this? One component that's directly in the opposite direction of my normal force, and then also one component that's directly parallel to the surface of my slope. These will be my F sub gy and F sub gx. Dallas?
Could you still do it like if theta was the 30 degrees and the F sub g was just your opposite angle?
You could do that, but the thing about it is that that's going to muddy up some of the trig because this vector would need to be longer than this line. So it doesn't really work in that sense. Ooh, my bad, guys. It doesn't really work in that sense. So what we can do instead is if we can recognize that this angle here is actually congruent to my incline, then it doesn't really matter. This angle is indeed congruent to the incline angle. So they're both 30 degrees. So that's why the trigonometry works out me drawing the triangle here like this. Okay? Brennan?
If that interior triangle for force of gravity is, that's a right triangle, right?
That is a right triangle.
Then could you just use the rules of 30, 60, 90?
Sure, you could. Yeah, absolutely you could. Yeah. But right now we don't know the magnitudes of any of these right now because we don't even know the mass. So yeah, you could, but it would make your algebra, it could potentially make your algebra harder or easier depending on how it's set up. Now, how do you find force due to gravity, just normally? Yeah, so I'm going to actually label that down here. I know that F of g is mass times gravity. Agreed? Mass times gravity. So that means that my normal force, and that's because the normal force is counteracting the vertical component. That means my normal force must be equal to mass times gravity times cosine of theta. Do you guys agree with me? Good, good, good. And the force that's pulling our skier down the slope must be, I'm going to label it as F sub gx. It must be mass times gravity times sine of theta. Do you guys agree with me? All right, this is pretty much going to be true. Notice that we haven't plugged in gravity. We haven't plugged in mass. We haven't really even plugged in a theta. So this is a general free body diagram that can be used for any incline problem. That's why we're doing this in the lecture. All right? Regardless of what the friction actually is, regardless of what the mass of the object actually is, we have a general free body diagram that kind of sets up the any general incline situation. So, the question is then, what is her acceleration? Have we decided that we have enough information to find her acceleration yet? Maybe, maybe not. Renee?
Okay, I don't know how it's so we should have this the first part, but if we were able, so if we have formula defines the F sub n, if we can use that as the kinetic friction thing to find the force of friction, and then we subtract the force of friction as the F sub gx from each other, that gives us our net force, and then we can use the mass of the skier to find her acceleration.
That's exactly right. Yeah, that's exactly. All right, so I'm going to go ahead and do what you just said. I'm going to go ahead and do what you just said. You said that we need to identify what the force of friction are in terms of the normal force and everything like that. So what I'm going to go ahead and do is I'm going to go ahead and plug in my point 1 here, but you need to be able to remember that the relationship is the coefficient of friction, 0.1, times normal force, all right? I have this in the way a little bit. Let me move it up, all right? Times normal force, which we have already defined normal force to be mg cosine theta, all right? And if we want to find the skier's acceleration, then we have to know a couple of things. First off, how do we normally find acceleration when we're dealing with forces? We use Newton's second law, right? So if we wanted to be able to find the skier's acceleration, normally we would need to be able to plug in two things to this formula, right? The force and the mass, okay? Now, we're not really given actual values for those yet. So we're going to have to try to see if we can maybe figure out a way of finding acceleration in terms of something, all right? So if we know we need the net force, and we can set that equal to mass times acceleration, but we don't have the mass, what we can do is we can try to decide what her net force is. And since there's not going to be any vertical movement, of our skier, we know that the net force must be downhill. Then we can calculate the net force by taking this, which is the force downhill, and subtracting this, which is the force uphill. All right? If I subtract this from this, then my result should be my net force. Do you agree? And so then I could say if what I'm actually dealing with here is F sub net, then I can say that F sub net must be equal to mg sine theta minus 0.1 mg cosine theta. All right? Everybody believe me and agree with me here? Good. Then I can set that equal to mass times acceleration. All right? And if I set that equal to mass times acceleration, then I've done something really cool because now I have an equation where there's three terms, okay? There's a term right here, mg sine theta. There's a term right here, 0.1 mg cosine theta. And there's a term right here, ma. There's an m in each one of those terms. And since there's an m in each one of those terms, I can go ahead and cancel out the m in each one of those terms. It's the same thing as dividing both sides by m, okay? So if I'm able to cancel out those terms, then what I'm left with is something that looks like g sine theta minus 0.1 g cosine theta is equal to a. So now I've gone ahead and I've solved for the acceleration of our skier in terms of g and theta. The thing is that we were given a theta. It's 30 degrees, okay? So we can just plug in 30 for theta. What's sine of 30? 1/2. So this is 1/2 g minus, what's cosine of theta? Root 3 over 2. All right. So root 3 over 2 times 0.1. Let's go ahead and do that one in the calculator, actually. Cosine 30 times 0.1. That's going to give me about 0.87 g. That's going to be equal to A. All right. And then all we have to do here is just go ahead and subtract 1/2 g by 0.87 g. All right, and then we get negative 0.37 g is equal to our acceleration. So we've now solved algebraically for the acceleration of our skier. And this isn't even in terms of anything but g, and we know what the value of g is, so we can go ahead and find what her acceleration is. So what's actually happening is she's slowing down. Am I correct? G is 9.8. Was that your question, Rocco? All right. Now, any questions? Awesome. This procedures that we just took, okay, is going to be an important one to remember. It's going to be an important one to use in problem 2 in our practice set. All right. And also just understanding that this free body diagram kind of works for any mass on an inclined plane that is experiencing friction. All you need to do is just plug in your own coefficient of friction, your own theta, your own mass, and you can pretty much solve any problem with this free body diagram if it's on an incline and it's experiencing friction. All right. Go ahead and get started on your practice problems. What's up, Maya?